Hey calculus class, today we are going to learn topic 54, integration with parametric curves. So, area underneath parametric curves. From earlier, we know that x equals f of t, y equals g of t, and y equals big F of x, which implies that g of t is equal to big F of little f of t. In order for us to find the area under the curve, we must integrate y equals big F of x, which gives us that the area is equal to the integral from a to b of big F of x dx. Now, if I go ahead and replace the x with little f of t, that means that my limits are going to change. So since we want to integrate with respect to the parameter t, we will need the limits to represent the boundaries of t, and we will need dx to somehow become dt. Well, we currently have that x equals f of t. Well, I can find dx by taking the derivative of f of t dt. So therefore, I can say that dx equals the derivative of f of t dt. And we are going to let t be between two values, alpha and beta. So now we can say that the area is equal to the integral from alpha to beta of big F of little f of t times the derivative of little f of t dt. Well, we know that big F of little f of t is the same thing as g of t. So therefore, we can say that the area underneath parametric curves is given from alpha to beta of g of t times f prime of t dt. So the theorem is if the curve is traced out once by the parametric equations, x equals f of t and y equals g of t, and t is between alpha and beta, then the area can be calculated by, and these are different forms, basically the integral from a to b of y dx, which is the same thing as the integral from alpha to beta of g of t times the derivative of f of t dt, when f of alpha is less than f of beta. And then basically we have the same thing, but your limits are switched if f of b is less, or sorry, f of beta is less than f of alpha. All right, so let's look at an example. So we want to find the area enclosed by the given curve. X equals cosine t, y equals e to the t, where t is between 0 and pi. All right, so the first thing I need to do is to check which endpoint is bigger or smaller on f. So I'm going to plug 0 into f. Remember, f stands for the x function. So that means I take cosine of 0, which gives me 1. And then I'm going to take cosine of pi, which gives me -1. So this tells me that f of pi is less than f of 0. So that means I'm going to set up my integral as beta to alpha of g of t times f prime of t dt. So when I do that, I'm going to need the derivative of f, which is the derivative of the x function. And then I leave g, or the y function, alone. So when I set this up, I'm going to go from pi to 0 of et times negative sine t, which is the derivative of cosine t, dt. Simplify that so I can pull out the negative. And then I don't have this on the PowerPoint, the work's shown out, but to integrate this, you should notice that you're going to have to do integration by parts. Do that, plug in the 0 and pi, and you will get e to the pi plus 1 over 2. And decimal form is 12.0703. All right, I want you to go ahead and try this one on your own. Let's see how we did. So first thing, I need to check the endpoints of t. So I'm going to plug into the x term. So I get 0. When I plug 0 in for t in the x, I get 1. When I plug in 1, I get 1 plus e. So this tells me that f of 0 is less than f of 1. So that means I'm going to set it up in terms of alpha to beta. So I'm going from 0 to 1, and I have my y function times the derivative of my x function, dt. And it's okay if you just want it to do that in your calculator, that's fine, or you can multiply through and do integration that way as well. All right, arc length of parametric curves. So recall our arc length formula, which is given by the integral from a to b of the square root of 1 plus dy dx squared dx. So since we now know that dy dx for parametric curves is dy dt over dx dt, we can write the arc length from alpha to beta of the square root of 1 plus dy dt over dx dt squared dx dt dt. All right, and the reason why we have dx dt dt is because we had to translate the dx over in terms of dt, and from earlier we had that dx is equal to the derivative of the x function dt. Now I'm going to do some simplifying to make this a little bit easier. So I can distribute the power of 2 through using my exponent properties and find a common denominator. So I have dx dt squared plus dy dt squared on the top all over dx dt squared. And then I can pull out the square root of dx dt. So here I have 1 over dx dt. And notice that the dx dt's cancel. So now I have the integral from alpha to beta of the square root of dx dt squared plus dy dt squared dt. So this leads us to the theorem that if a curve C is described by the parametric equations x equals f of t, y equals g of t, where t is between alpha and beta, where f prime and g prime are continuous on alpha to beta, and C is traversed exactly once as t increases from alpha to beta. So that just means that it crosses once. Then the length of C is given by the following integral. And if you wanted to rewrite it as the square root of the x function, the derivative of the x function squared, plus the derivative of the y function squared, dt. Note, a curve is traversed only once when a particle traces the curve only once. In other words, the particle is strictly moving in one direction. We can look at dx dt, and if the sign does not change for the values of t, then the particle is moving in only one direction. All right, so let's take an example. We want to find the arc length of the given curve, x equals t cubed and y equals 3t squared over 2, where t is between 0 and the square root of 3. So first thing I'm going to do is take the derivative of dx dt, so 3t squared. Derivative of dy dt gives me 3t. And then I'm going to go ahead and set up my arc length. I'm going from 0 to the square root of 3. And of course you check your limits by plugging 0 and the square root of 3 into the x function. And you'll notice when you do that, you will get that 0 is the smaller one. And then I have my derivative, the square root of the derivative of dx the derivative of the x function squared plus the derivative of the y function squared dt. And then at that point, I can simplify it. So I use my exponent properties. And I can factor out a 9t squared. And using my square root properties, I can take the square root of 9t squared to give me 3t. And then I can use u substitution to integrate this, and I get 7. All right, speed and distance. So speed, we currently know if the position of an object moving along a straight line is given by the differentiable function f of t, then the object's speed is given by the absolute value of f prime of t. However, with parametric curves, we have that the position of the particle is given by f of t comma g of t, which means we have two components to its speed. So the first component is that there's a horizontal component given by the derivative of f of t. And then we have a vertical component, which is given by the derivative of g prime of t. So we have our horizontal, and we have our vertical. And this is our f prime of t, and the vertical is g prime of t. And this, from this point to this point, represents our speed, which is given by our arc length. So we say that, or sorry, not the arc length, it's our integrand of the arc length. So we say that speed is equal to the square root of f prime of t squared plus g prime of t squared. And distance, we currently know that if we want to calculate the total distance traveled by a particle, we would integrate the velocity function. So with parametric curves, we know that the speed is given by the square root of f prime of t squared plus g prime of t squared. Therefore, we can calculate the distance traveled by taking the integral of the speed. And yes, this is the arc length formula. It should make sense that the total distance the particle traveled along the curve is the length of the curve. All right, so let's take an example, but AP style, for the speed and distance. So an object moving along a curve in the xy plane is at position x of t comma y of t at time t, with dx dt equaling arc tangent of t over 1 plus t, and dy dt equaling the natural log of t squared plus 1, for t being greater than or equal to 0. At time t equals 0, the object is at position -3 comma -4. So part A says to find the speed of the object at time t equals 4. So that means I'm going to use the square root of the derivative of x squared plus the derivative of y squared. And this problem was really nice. It gave us the derivatives of x and y for us. And since I want it to be at t equals 4, I plug 4 in for t, and you would use your calculator to eventually evaluate this. And this would be a calculator question. Since there are no units in this problem, there are no units for you to put on your answer. All right, for part B, it says find the total distance traveled by the object over the time interval from 0 to 4. So that means I'm going to integrate my speed from 0 to 4, and this would be something that you would use your calculator for, and you would get 6.423. And then part C says to find x of 4. Well, this means at what x value is the particle after 4 seconds. So since I want just where the x value is, I don't care about the y value. So that means when I integrate my speed, I'm only focused on the horizontal component. I am not worried about the vertical component. So that means I'm going to have where I start at x of 0, plus how far I moved horizontally only from 0 to 4. So I'm only going to integrate my x component. And at the beginning of the problem, they did give you the initial starting point when t equals 0, and you're only going to use the x component of that point, which was -3. And you can use your calculator to evaluate that, which gives you -0.892. Well, I hope you enjoyed learning about the integration of parametric curves, and I will see you in class tomorrow. Have a good night.